Okay, so now we're going to define what it means to perform substitution within a formula. So we're going to define this operation of substitution, and we're going to denote it in the following way. So first, the one thing that we need to note is that this is what we call a schema in the meta-theorem. It's sort of like a string in the meta-theory, and the reason we know that it's in the meta-theory is because it doesn't contain any symbols from our Boolean alphabet. Right? Both of these are variables within the meta-theory that are called string variables. So they're meant to represent strings made from elements of our Boolean alphabet. These brackets are different from the round brackets that are in our Boolean alphabet. And the colon and equal sign are also not members of our alphabet. Moreover, notice that this P is a bold P, and so that is also not a member of our Boolean alphabet, but it is meant to stand for any possible Boolean variable that we could put in here. So a bold P is a meta variable because it's meant to take the place of any possible Boolean variable instead of simply the Boolean variable P. Okay, so now that we've gotten that out of the way, let's get an idea about what this operation is meant to do. Well, simply, this means that we want to substitute or replace every Boolean variable P occurring in the formula A by the formula B. So wherever we see the variable P within A, we just want to replace it with B. So it's a very simple, intuitive thing to do, but of course, as you know, in this introductory course on logic, we need to make things very formal in order to ensure that they don't provide contradictions or paradoxes, and so you will see that the definition is looks much more complicated, but essentially all you need to think about is wherever you see a P and A, you replace it by the formula B. Okay, so as we mentioned, this is a schema in the meta-theory, but it's meant to stand for the string, and in fact we'll see it's a well-formed formula we get after performing this operation. So even when we are working within logic, we're going to see this schema being used, sort of like we're going to see string variables being used, sort of to take place for the well-formed formula that is formed by performing this operation. Some other important things about this operation is that it has the highest priority over all Boolean connectives. So, for example, if we're considering our least parenthesized notation and this schema appears within our well-formed formula, we know that we need to perform this operation of substitution first before applying any of the other Boolean connectives. And we'll see examples of this in class. And finally, the other thing that's important is that it's in fact left associative instead of right associative. So all of the other Boolean connectives we recall a right associative. That means the right one X first, which means we put the brackets around the right one first. In this case, because of the nature in which we apply substitution, it's left associative. So we would put brackets around the left occurrence of this operation before the right one. And we'll see examples of this in class as well. Okay, so now that we have an intuitive sense of what this means, and I think you should really hold on to that, let's formally look at how to define this operation. So here is a multidimensional definition, right? In order to formally define this operation, we need to define how to apply it at each stage of a formula calculation. So that's what's happening here. But essentially all you need to think of is whenever you see P and A, you replace it by the formula B. Okay? So let's see exactly how that works. So in this case, our first case is to consider all the atomic formulae. So suppose A is an atomic formula. It could be the variable P. If A is P, then we know here's P, we replace P by B, and this is why this well-formed formula, this string becomes the formula B. If A isn't P, then, and it's an atomic formula, then it's either a different Boolean variable Q, or it's one of the constants top or bottom. In this case, notice that P doesn't occur in A, and so simply the formula remains unchanged. We just simply get A back. Okay, so that takes care of the atomic formula case. The next step in constructing a formula is to consider A as not C for some well-formed formula C. So in this case, we just apply the rule that substitution is of highest priority. So we simply apply substitution in C. So wherever we see P and C, we replace it by B and then add the negation sign. Then we negate that substitution. And this is a recursive definition, so to define this, we go back through this definition, and essentially all this is telling us is when we see P, we replace it by the well-formed formula B. Finally, the last step of our formula calculation is that A is of the form C circle D, where circle is any of our Boolean connectives, our binary Boolean connectives. So in this case, again, substitution has the highest priority, so we apply substitution to each of these well-formed formula C and D, and then connect them with the corresponding connective. And again, all of this boils down to wherever we see P in either C or D, we replace it by B. Okay, so one of the main reasons that we need to formalize the substitution is to ensure that when we perform substitution, we get back a well-formed formula. So that's essentially why we define it within this way. And so this leads us to two very important statements. The first one is essentially that for any formula A and B and Boolean variable P, the substitution we've performed is in fact a well-formed formula. And this is provable by induction and is proved by induction in the textbook. And the other natural proposition or natural result that occurs from this is that if P doesn't occur in A, then the substitution simply remains unchanged. We simply get A back. And this is also easily proved by induction in the textbook. Okay, so that brings us to the end of section 1.3, and now we're going to move to section 1.4, where we begin to work within logic and develop our system.